Okay, watch and listen carefully here, guys. So on our first one here, we got a large rock that's rolling down a hill towards the road. Okay, the driver first sees it moving at 7.5 meters per second. That would be our what? Initial velocity. Okay, when the rock reaches the road, it's traveling at 13.5. That's our final. Okay, it's accelerating at 4.4 meters per second squared. So that's A. How long does the driver have to stop? What are we looking for? Time. Okay, so give them a mark for their givens. You can give them a mark if they wrote the acceleration formula down. That's kind of a gimme, but we'll give it to them anyway. Okay. Then we got to manipulate for time. So we multiply both sides by t. Okay. So multiply both sides by t. T comes over here. Then we divide both sides by a. A comes underneath. So if they have this manipulation, give them a mark. Numbers plugged in, give them a mark. If they only did one or the other, just give them both. Okay. And then our final time is 1.36 seconds. If they rounded that differently, like to only one decimal place, that's fine. Just okay. Questions on that one? Okay. In general, I would like to see 2 decimal places. Okay, just so that we're all kind of clear on that, I'd like to see 2 decimal places. Okay. All right. Moving on to the second one. So Wile E. Coyote drops an anvil in attempt to catch the roadrunner. If I drop something, how fast is it going at the beginning? 0. It's a little trick, okay? If you drop something, like right now, I'm holding this pen out. How fast is it going? 0, and it'll be going 0 when I let it go too. Okay? At least for that instant when I first let it go. So anytime you see the word drops or falls, okay, or something like that, it implies that VI is 0. All right, so VI is 0. All things on Earth accelerate at 9.81 meters per second squared. That's on your sheet. It's on your formula sheet. Acceleration due to gravity. Okay. VF is the thing we're looking for, and time is 6.5 seconds. So we got A equals VF minus VI over T. Give them a mark for that. The manipulation for VF means I multiply both sides by T, and then I add VI to both sides, okay, to give me VF. Well, VI was 0, so it doesn't really matter. Okay, but you can give them a mark for the manipulated formula, a mark for plugging in the numbers, okay, and our final velocity, or sorry, how fast is it going? It's not asking for velocity, it's asking for speed. So I don't have to put down on my answer because it didn't ask for velocity. Okay, 63.8 meters per second. If they had down on that, I'll let it go this time, but in the future, if it doesn't ask specifically for velocity, we don't have to put it on. Okay, all right, so it's out of 10. Give them a mark out of 10, let them see it, put it in the box. Okay, so for a question like this, okay, where we're given a number that's in scientific notation, okay, it's just like Avogadro's number, if you recall back in chemistry, okay, if I'm going to punch that into a calculator, I do it like this, okay, so I use, first off, bracket, you got to enclose that number entirely in brackets, then it's 2.5, hit the second function button and then the comma. Okay, because above the comma are the 2 capital E's that stand for times 10, and then whatever number you enter after that is the power. Okay, you do that, and then you divide by 8,000. All right, and that gives us, whoop, by 800, not 8,000. So it would give you 1 extra 0 on there. Sorry, delete. 312,500 seconds, all right? So when you're punching that into your calculator, whether you're using your phone or not, okay, it's all the same. Enclose in brackets the number, then the EE button, however that is on your calculator, 8, close the brackets, okay? If you're doing that on your phone, usually when you close the brackets, it actually spits out the real number as opposed to leaving it in scientific notation, okay? And then just do whatever operation you need to do after that. Okay, so we got this particle that's moving with an initial velocity that is positive, so let's say to the right, okay? The particle has no acceleration until time 3 seconds. So what is it doing for the first 3 seconds? It's traveling at a constant speed, okay? So in part 1, okay, I know that my acceleration is 0, okay? But my speed is 112, positive 112 meters per second, and the time is 3 seconds. Okay. The particle, after 3 seconds, the particle has an acceleration, okay, of -4 meters per second squared. Okay. And what's the velocity after 16, at time 16 seconds? So how long does this second part take? It traveled at a constant speed for 3 seconds, and they're asking me how fast is it going after 16 seconds? How long did part 2 take? 13 seconds. Really a tricky read. Okay, it's a question that's just a tricky read. All right. What's the initial velocity for part 2? How fast is it going when part 2 starts? 112 meters per second. Again, tricky read. All right, it's just a matter of really picking apart the wording of a question so that we know what's going on. All right, so we're looking for VF here. So really, is any of this stuff important for my calculations? Not really. Okay, only that I need to know that this part took 3 of the 16 seconds, so I got the time right over here. Okay, all right, so now that I know that, I'm manipulating for VF. So A equals VF minus VI over T. So I multiply both sides by T. I add VI, and I'm calculating VF. So VF will be positive 112 plus 13 times negative 4. All right. So when we punch all that in, we'll have 112 plus 13 times negative 4. Should give us 60. Okay, everyone follow me there? Most common mistake is to enter 16 seconds for the time. Okay, on that question, that's the most common mistake. And I think usually you get like 48 or something like that if you have the 3 extra seconds. Okay, everybody with me there? Okay, any other ones giving us trouble? How many people are done? The whole thing? How many people are close? All right, good. All right, I'll give you about another 2 minutes or so, and then we're going to move on. Expect that on a unit exam, you would probably have an acceleration problem as part of the written response. Okay, that would certainly be something that I would assess. So make sure that you're familiar with how that formula works. Okay, all right. Thing we got to look at now is, in my mind, because I'm a physics guy, the most important concept there is in high school science. Okay, and that is the work-energy theorem. All right, we've kind of talked about it a little bit on like the first and second day, but we got to go into now the nuts and bolts of it. All right, work-energy theorem tells you what happens to energy. Okay, you can't create energy, we know that. You can't destroy energy, we know that. Okay, what happens to it? Okay, because sometimes it looks like it's destroyed, sometimes it looks like it magically appears. Okay, but it doesn't. Energy is always brought in from somewhere and transferred away to somewhere else. Okay, that's what makes it look like it's created or destroyed sometimes. Okay, but anytime it's transferred in, what do we call that? What's being done if mechanical energy is being transferred into a system? 4-letter word. Keep your minds out of the gutter. Someone said it. Work. Okay, work is being done. Okay, work's a 4-letter word, by the way. Okay, just so you know. It is, really, in all respects. Okay, so if I do work on a system, I'm transferring energy to it. Now that system has more ability to do what? Same word. Work. Yeah, okay. Energy is the capacity to do work. So if I do work on something, I'm giving it energy. Now it can do more work, right? It's like this. You go to the gas station because your car is empty. You fill it up with gas. Can it go now? Okay, well, what did you do? You just filled it up with chemical energy. Now it has the capacity to do work. Okay, it can drive you from place to place. For some reason, it doesn't work when the tank is empty. Okay, it's very frustrating, but it doesn't. All right. When your car is driving you around from place to place, okay, it's taking that chemical energy, it's turning it into mechanical energy, as well as what? Heat, sound, all kinds of other forms of energy that are not doing work. Okay, they're transferring away to the environment. Okay, so work-energy theorem deals with just the mechanical energy parts. Okay, just the work coming in, the work going out, and we simplify it quite a bit. Okay, we don't deal with real-world situations where energy is lost to the surroundings. We assume everything is 100% efficient, and that all the energy that comes in is used to do useful work. It just makes things a lot easier. All right, so perfect utopian physical world is what we're going to deal with. Okay, work-energy theorem can be summed up simply like this. Work is a change in energy. Okay, that could mean a transfer in or a transfer out. Either one is a change in energy. That's delta, by the way. It's supposed to look like a triangle, but my penmanship is awful. I can't even make shapes unless I really concentrate. Okay, so delta E. Okay, and anytime we're calculating change, what are we really doing? Everywhere on your formula sheet where you see delta, after that it shows, okay, a letter, and then after that usually it shows equals, and then final minus initial. Delta always means final minus initial, right? So it's the change in energy. Now, if you're going to do mechanical work, what do you usually have to do? If you want to transfer energy to something, what do you usually have to do? Okay, yes, you would have to have your own energy because energy is the ability to do work. I was actually thinking simpler than that, actually. Move. Yeah, okay? You have to move. And when you move, you're usually exerting a what? A force, exactly. Okay, I can't do work unless I'm pushing, pulling, lifting, throwing, doing something, okay, where I'm exerting a force on another object, okay? And the key part of that is that that force results in movement, okay? I mean, if I sit here and this hole punch is right here, and I pull on it, but I don't pull hard enough to lift it, did I do any work? No, I didn't. Did the hole punch's energy change at all? It didn't. If I don't make it move, I don't change its energy. Okay? Now, I can change its energy in two ways. I can change its potential energy, or I can change its kinetic energy. Right? If I just pick it up and lift it straight to here, I've changed its potential energy. If I throw it, which I'm not going to do, okay, then I would change its kinetic, okay, because I would increase or change its speed. Remember, kinetic energy is dependent on speed, and potential energy is dependent on how high above the ground you are if we're dealing with gravitational potential energy, which we are. Okay, so work-energy theorem, okay, work and energy can be equal, but one cannot exist without the other. I mean, if work's a change in energy, then mathematically it says right here that they're equal, okay? Understand both kinetic and potential, that's what we just reviewed there, okay, and understand the relationship between force and work. Okay, pretty simple relationship. If I exert, let's say, 10 newtons, newtons, by the way, are the units for force. Okay, if I exert 10 newtons of force on this rolling chair, okay, I'll do a certain amount of work. If I exert 20 newtons of force on this, how much more work will I do? Double. Yeah, it's a linear relationship. If I use twice as much force, I'm going to do twice as much work, assuming everything else stays the same. Okay, so it's a linear relationship between force and work. The more force I exert, the more work I'm going to do. Okay, so that's the other part of work. Work is force multiplied by distance. Okay, we said you have to exert a force, and it has to result in a movement. Okay, either it's up and down, or it's side to side, but it's got to move. All right, so force times distance equals work. Work's a change in energy, so force times distance equals a change in energy. Okay, it's just several formulas kind of all set together. Okay, so energy, just like any of the other things we've been dealing with, acceleration, velocity, displacement, so any kind of motion, is a measurable quantity. Okay, specifically energy is a measure of an object or a system's capacity to do work. Okay, if I'm holding a heavy object above my toes, it has potential energy, because if I drop it, it will change the shape of my feet in an undesirable way. Okay, changing the shape of something counts as work. All right, you exerted a force through a distance, whatever distance the part of the object that had its shape changed moved. Okay, and that counts. All right, I mean, if you were to, not that you would do this, but swing a bat at a wall or something like that, then when you hit it, you would leave a dent in it. Okay, well, you've done work. You've changed the shape of the wall. Okay, not the whole wall, but part of it. All right, Work is a transfer of energy from one object or system to another. Okay, how many of you have ever set up a mousetrap before? Okay, I mean, they're coming out with all new designs, but this still works. Okay, now, this design is a prime example of work and energy being transferred around. Okay, when it's not in this position, when it's in the executed position, so, okay, does it have any energy at that point? No, because now it can't snap, right? Once it's already snapped and the killing bar is down on that's actually what it's called, okay? When it's snapped over and the killing bar is here, okay, it can't do anything else now, can it? Okay, so it has no energy in that position, no ability to do any more work. If, however, I grab the killing bar, okay, and I raise it back over here, now what does it have? It has potential energy, elastic potential energy, because I've exerted a force, pull, through a distance, however far I move that, okay, and now I've transferred potential energy to the mousetrap. Okay, then, okay, we put the locking bar into the trigger, okay, and now this system has the ability to do work. All right, now, when the trigger is activated, okay, the locking mechanism releases the killing bar, which swings over, and yeah, hopefully humanely and very quickly, okay, kills the mouse. All right. Now, when it does that, is there a sound? Is sound a form of energy? Okay, prime evidence then that there was energy stored in the spring. Okay, so it snaps over. Okay, if you've ever dry fired one of these, you don't use your finger. Just a tip. Okay, use like a stick or something, right? And if you hit it right, I mean the mousetrap flies right off the ground. Okay, when I used to teach Science 24, which is kind of the non-academic grade 11 science. Okay, we used to make carts that were powered by mousetraps. Okay, and we would just always have them on the back of the cart, and we would set them up like this, and then you just trigger it, and the killing bar would smack against the wall, and it would shoot the cart away. Okay, and we would see whose could go the farthest. Okay, to demonstrate that, yeah, there's energy in here. In fact, we would use how far the cart traveled to calculate how much energy we put into it. All right, it wasn't really accurate, but it was a decent, at least approximation. All right, does everyone follow me there? So I exerted a force through a distance, and that put energy into the mousetrap system. Yeah? Okay. That's the key thing we got to realize. Okay? Force times distance equals a change in energy. Whoop, not change in work, change in energy. Okay? And the reason that there was a force and a distance and a change in energy is because I did work. Work-Energy Theorem. It's as simple as that. Okay? That's the Work-Energy Theorem, but it's the most important concept in science. All right. When you hit a tennis ball, same idea. Okay, when you hit a tennis ball, okay, you are exerting a force through a distance on the tennis ball. What kinds of things influence how fast you can hit the tennis ball? Speed of the racket. So partly your strength. Okay, what else? How tight the strings on the racket are. We'll simplify and say that the racket is solid. Okay? Yep, the weight of the racket certainly plays a part, yep. Although, what are they doing with rackets all the time? Making them lighter. Why? Right. Can you swing a light racket faster? Yeah, okay. Now think about this. This is the formula for kinetic energy. We haven't got this far, but it kind of fits here. Okay? Mass and speed influence how much kinetic energy you have. Which one has a bigger impact? Mass or speed? Speed, because if I double my speed, it's squared. Okay? I double my speed, I'm going to have how many times more energy? 4. Right? 2 squared is 4. All right? So it's exponential. If I can increase my speed, that'll have a bigger effect than swinging something heavier. All right? Everyone follow me on that one? Okay? So it's an important reason why we design lots of sports implements to be lighter. Okay? The only sport that has not embraced that? Baseball. They have embraced performance-enhancing drugs instead. Okay? If you are a roid monkey, you can swing the bat faster. Okay? So we're going to keep using a big piece of tree and we'll just use anabolic steroids and get huge, okay? Sorry, I have no respect for baseball whatsoever. I can't stand to watch it. It's 3 hours of watching two guys play catch. Yeah, I don't get it. Anyway, same with soccer. I don't get soccer either. Okay. All right. Sorry if any of you are insulted by that, but all right. So that's the big deal here. Speed is a big deal. So, how long during the serving part of a tennis swing? How long can I do work for? Yeah, for how long during the swing? How long am I changing the energy of the tennis ball? Yeah, because that's what I'm changing, right? Like I throw the tennis ball in the air, but I'm not worried about the throwing part. I'm worried about when I hit it, okay? When it's actually in contact with the racket, okay? I can't do any work on the tennis ball unless it's in contact with the racket, which I'm moving, all right? So if work is force times distance, there's two things I can do to increase the speed of the tennis ball. I can get stronger so that I can exert more force, baseball mentality, okay? Or I can improve the equipment and my technique so that I'm exerting this force over a greater distance. Okay, this is exactly why. Remember, I said simplify, right? Okay, why I said simplify the racket so that it's just a solid thing. But rackets aren't solid, are they? They have strings. You ever seen what happens to a tennis ball when it hits a racket? It actually, if you could stop the racket and you could see it just at the moment where it's in contact, the tennis ball and the strings are back here, behind the frame of the racket. Okay? Because the longer I can keep the tennis ball on the racket, the longer I can exert force for. So this number gets bigger, this number gets bigger. If this number gets bigger, I'll have a greater change in energy, and as a result, the tennis ball will go faster. Okay? Most sports have completely embraced that idea. Okay? Change technique, change equipment in order to improve people's ability to transfer energy. Hockey is another example. Okay? Back in my day, a hockey stick was a piece of tree. All right? It was not overly flexible. It had some flexibility, okay? But it was basically just a big heavy chunk of tree. Now, what are hockey sticks made out of? Yeah, fiberglass or carbon fiber and graphite, things that are flexible. Okay? Why? Because when you use a hunk of tree, you have an arc about that big where you're in contact with the puck. Okay? But if you've got a stick that flexes, now that arc goes all the way out to here. And on the finishing end, you have the elastic rebounding effect where it snaps forward. Look at the extra distance you gain. Can you hit the puck faster? Absolutely. Okay? Then it doesn't just become about strength, it becomes about technique. Okay? And your ability to exert that force that you can exert over a greater distance. Okay? Golf, another sport where they're doing that. Okay? I mean, we've made the clubs lighter and lighter and lighter so we can swing them faster. Right? But we've also changed the technology within the ball. Okay? When I was young, hitting a golf ball hurt. Okay, because golf balls were rigid and hard, and when you smack them with the big chunk of wood, that's where the term woods comes from. Incidentally, woods aren't made out of wood anymore. Okay, you could feel the vibration in your hands. Okay, you knew when you hit that ball. Right now, the shell that makes up a ball is made of softer materials. Okay, so that the ball actually squishes and flattens out against the club face. And if it does that, it stays in contact with the club face just a little bit longer, which increases the distance over which I exert my force. All right? Now, also back in my day, people's swings were all different. Okay? When you watched professional golf, you knew exactly who you were watching even if you couldn't see their face. Okay? Because everyone's swing was very unique. Now, everybody's swing looks the same. Okay? Because we've polished up and we know how, here's the best technique, here's the best swing pattern to use because it'll result in more energy transfer to the ball. Okay? It all comes down to physics. Okay? All of that stuff is about physics. Okay? And all of our sports are kind of embracing that science. They're also embracing it in safety. Okay? If I want to prevent injuries, I want to limit how much energy gets transferred over. Agreed? Okay? So we've designed padding to be different, helmets to be different. Okay? Things that will protect your brain. We'll talk about all that stuff tomorrow. Okay.